linear and exponential models. So first, let's just start out with a quick review of linear functions. Linear functions often take on the form y equals mx plus b, or f of x equals mx plus b. That is the slope-intercept form, famously called that because we can see the slope m and the y-intercept b directly in the equation. Now recall, linear functions have a constant rate of change. Now what does that mean? Yes, it means that the slope is a constant number. So in my example, y equals negative 2x plus 5, the rate of change is negative 2. The slope is negative 2. But what exactly does that mean? Let's make a table for this function and pick a couple of values of x and get some values for y. So if x is 0, y is 5. If x is 1, negative 2 times 1 plus 5, that's 3. If x is 2, y will be 1. If x is 3, y will be negative 1. If x is 4, y will be negative 3. Now let's look at this table. So on the left side of the table, I have x going up in increments of 1. All the way down the table here, from 0 to 1 to 2 to 3 to 4. X is going up by 1. But what's happening with the y values? Y is going down by 2. So when you say that this function has a constant rate of change of negative 2, when you say that the slope is negative 2, what that really means is that each time x goes up by 1, y will go down by 2. So if you increase x by 1, the y value is going to decrease by 2. That's sort of what it means to have a constant rate of change, and that will happen for any point that you're standing on this function. So if I pick the point 3, negative 1, if I increase the x value by 1, if x goes from 3 to 4, then y is going to go down by 2. See, from negative 1 to negative 3, y went down by 2. So that's sort of an interpretation of what constant rate of change means. So all linear functions have a constant slope, a constant rate of change. So that means every time you increase x by 1, y is going to do some either increase or decrease by some fixed amount. Now let's compare that and contrast that with exponential functions. So y equals a times b to the x. There's the basic exponential function where a is the initial value and b is going to be our common ratio. So the function is going to grow or decay based on what this common ratio is, based on what the base value is. And the function is going to grow or decay by a constant percentage. So the function grows or decays, that should say by, not b, by a constant percentage. So let's see what that means, because when a function is growing by a constant percentage, that does not mean that the function has a constant rate of change. And that's kind of a confusing idea. So let's look at a table for this exponential function. So when x is 0, 1.25 to the 0 is 1, times 300 is 300. And that's when x is 0. Then, it's hard for me to do a lot of mental math with this function that I picked. So I'm looking at the table in my calculator here. When x is 1, y is 375. When x is 2, y is 468.75. When x is 3, y is 585.94. So like, when x is 3, you would just do 1.25 to the third power, get that result, times that by 300 to get that 585.94. So I didn't do those in my head. Except for the first one, the 0, 300. The rest I was just looking at my calculator. Okay, great. So now let's see what's going on here. This function definitely does not have a constant rate of change. Because see, on the left-hand side of my table, what are the x values doing? I've purposely made the x values going up by 1. So now, if this function had a constant rate of change, then every time x increased by 1, y would have to increase by the same amount. But that's not what's happening. See, the first thing that happens here is that y goes up by 75 when x changes from 0 to 1. But then when x goes from 1 to 2, when x goes up by 1 again, y is actually increasing by 93.75 to go from 375 to 468. And then when x goes from 2 to 3, when x goes up by 1 again, y increases by 117.19. So this function definitely does not have a constant rate of change because as x is increasing by a constant amount, but y is increasing by an ever-increasing amount. So if this function had a constant rate of change, every time x would go up by 1, these y values would have to go from 3 to 375, then it'd have to go up by 75 again, then by 75 again. But that's not what's happening. When x goes from 0 to 1, y goes up 75. But when x goes from 1 to 2, y goes up by 93.75. And when x goes from 2 to 3, y goes up by 117.19. So the rate of change here is increasing. But the function is increasing by a constant percentage. So what's going on here is that this growth factor is 1.25. So to figure out the percentage that you're increasing or decreasing, you need to look at how much this growth, this base value, this common ratio, this growth factor or decay factor, how much bigger or smaller is this factor than 1? So this is 1.25 is 0.25 bigger than 1. So this is a 25% increase each time in y. So when x goes up by 1, y goes up by 25%. So the way that this is working is you would take 25% of 300, which is 75, and you would add that on to the 300 to go up to 375. So when you go from 300 to 375, that's a 25% increase. Now, when you're starting at 375 and you go up by 25%, you're going up by 25% of 375. So 25% of 375, that's a bigger number than 25% of 300. Because 375 is bigger than 300. So when you take 25% of 375, that's more stuff. So you're going up by a constant percentage means that as x increases, the increase in y gets bigger and bigger and bigger and bigger, even though the percentage that you're going up is constant. So another way to phrase this would be to say, like instead of saying when x goes up by 1, y goes up by 25%, you could say when x goes up by 1, y goes up by a factor of 1.25. By a factor, like that word, when you see that word factor, that usually indicates that there's some sort of multiplication going on. So to get from 300 to 375, you would multiply by 1.25. To get from 375 to 468.75, you would multiply by 1.25 again. So again, when you're going up by a constant factor, like that factor is constant, but the rate of change is not constant. Because if you're sitting at the 468.75, you multiply that by 1.25, that's going to be a bigger increase than when you multiply that 300 by a 1.25. So exponential functions are a little bit trickier than linear functions because the rate of change is going to be ever increasing in the case of a growth function, or ever decreasing in the case of an exponential decay function, even though you're going up by a constant percentage even though that you're going up by a constant factor every time x increases by 1. That does not mean that the rate of change is constant. So let's look at some specific examples and see if we can pick out some keywords here. So here we've got this newborn calf. It weighs 40 kilograms. That's the initial value for the calf. Each week, the weight increases by 5%. So that's going to be exponential growth because the weight's increasing, and we're increasing by a constant percentage. So that's going to be an exponential growth factor. So we can get rid of the choices. This function is linear, this function is linear, so like that choice is out, that choice is out. So now this function is exponential because w increases by a factor of 5. No. When you increase by 5%, you're increasing by a factor of 1.05 because you want to think of that base value as being how much bigger than 1. It's going to be 5% bigger. So your base value there is going to be 1.0. That's the factor you're increasing. So you're increasing by a factor of 1.05. That's the same as increasing by 5% each time x goes up by 1. Or in this case, each time t goes up by 1, each time a week passes by. So that would be the correct answer there. If you're increasing by a factor of 5, you'd be going up by 400% each time. It'd be a much higher increase. Okay, similar question. An iceberg floating in the North Pacific weighs 80 metric tons. So 80 metric tons is the initial weight of the iceberg here. Each month it loses 5 metric tons. So 1 month goes by, it would be 75 metric tons. Then another month goes by, it'd be 70. Then another month, 65, and so on and so on. So that is a linear decrease. That's a constant rate of change. Each month that passes, you're losing the same amount of weight. So the slope here would be 5. 1 month goes by, you would lose 5 metric tons. The slope would be negative, -5 because you're losing 5 tons every month that goes by. So now we can get rid of the choices that say exponential. This function is linear because w decreases by 5 each time t increases by 1. That is definitely the answer. What does this last choice say, though? The function is linear because w always decreases as values of t increase. Okay, that's true. W decreases when t increases because as time passes, this iceberg is weighing less and less. But that's not why the function is linear. So notice how this answer is phrased. This function is linear because... So while that statement is true, that's not what makes the function linear. Because just because a function is decreasing doesn't mean that it's linear. You could have a decreasing function that's nonlinear. So the function is linear because as t goes up by 1, as you increase 1 month, the weight goes down by 5 metric tons. It's a constant rate of change. I think we've got one more example here. So now we've got a bunch of choices, and we can choose linear or exponential. So the number of hours that you work each day decreases by 1.5 hours. So that is a constant rate of change. Every day you work 1.5 hours less. That's linear. The production of corn ethanol in Iowa increases by a factor of 1.9 every 2 years. So that means your years go up by 2, and you're going to multiply your output by 1.9. So you're increasing by a constant factor, but that means that the rate of change is going to be increasing over time. It's not a constant rate of change. Be exponential. The traffic cop writes 25 speeding tickets every day. That's a linear function. That'd be a constant linear function because as the days increase, the number of traffic tickets doesn't increase or decrease at all. So that would just be a constant function. The rate of change there would be 0. You increase a day, he writes 25 tickets. You increase another day, he still writes 25 tickets. So the slope there would be 0. 0 tickets per day. Day goes up by 1, but he's not writing any more or less tickets. So constant functions are linear functions. with a rate of change of 0. The population of Detroit, Michigan decreases by 8.5% every year. So when you're increasing or decreasing at a constant percentage, we've seen, that function is exponential. So there's a bunch of examples, and good luck as you tackle these word problems and applications.